Okay, a very good morning to all of you. So in today's session, I am going to introduce you with the new concept that is non-deterministic finite automata. And in short, we can call it NDFA, and sometimes we also call it NFA. So let's start. So I already told you that an NDFA is different from DFA. And how it is different, that for NDFA, if you start from any particular stage, for example, if you start from Q naught, right? So if for Q naught, you pass it the input 0, then there are two states that can be reached. There can be two output states. Here, as you can see that if to Q naught, if I give it an input 0, right? So it will take me back to Q naught also. This is one possibility. Another possibility is that if to Q naught you pass 0, it will take you to Q1, right? So any finite automata in which from a current state, if on passing some inputs, more than one state is generated as an output state, it means this is known as non-deterministic finite automata. And this thing we have already discussed, right? So in NDFA, for a particular input symbol, for example, here if the input symbol is 0, right, the machine can move to any combination of the states in the machine. For instance, here the machine can move to Q naught also, the machine can move to Q1 also. It means there are more than one state that can be reached if you provide 0 input to state Q naught. Okay, so in other words, the exact state, right, the exact state to which the state your machine moves cannot be determined, right? And here you can see that you can't determine that it should move from Q naught to Q naught or it should move to Q1, because there are two states that can be reached and you are confused. And if you are not sure and you are not able to determine that which state can be reached, which state should be your output state, it means that automata is non-deterministic automata, right? And I told you that like your DFA and NDFA can be represented by a set of 5 tuples, where Q is a finite set of states, all the states that your automata has. For example, if you take this automata, so it has Q naught, Q1 and Q2, 3 states, right? So your Q is made up of Q naught, Q1 and Q2. Then what is this summation? Summation is a finite set of symbols. For instance, here all the input alphabets, they are in summation. So your whole finite automata is made up of how many input symbols? 2, either 0 or 1. Okay. Similarly, the transition function sigma is the only difference that is there in between your DFA and NDFA. Okay, so I told you already that in case of DFA, if for any state Q, you provide it any input alphabet, it will take you to Q in case of DFA. But in case of NDFA, for any state, if you provide it any input, it will take you to any combination of all the other states. It means 2 raised to power Q. Okay, 2 raised to power Q means if there are 3 states, 2 raised to power 3 means 8 states can be generated. Okay, how I am saying that 8 states can be generated? If I talk about this Q naught, from Q naught you can move to how many states? There are possibilities that from Q naught you can move back to Q naught. If there is 0, there is possibility that you can move back to Q1. There is possibility that you can move to Q2 also. Okay, so from any one state you can move to that state and to other states. Okay, so for this example, you can move from Q naught to Q naught 1. That is one possibility. From Q naught you can also move to Q1, second possibility, and then from Q naught you can also move to Q2 in some scenarios. That is 3 possibilities are there if I am talking about Q naught only. Okay, and if I talk about Q1, again 3 possibilities are there. You can reach back here, you can reach here, you can reach here, total 3 possibilities. And if I'm talking about Q2, okay, so again how many possibilities? 3 possibilities. Okay, so in total there are almost 9 possibilities. right? So that's why I am saying that you always write it one less than the total number of possibilities, that is 2 raised to power 3, that is 8 and not 9. This is how this is generated, 2 raised to power q. Okay, I told you that it should not be considered as 2q, it is 2 raised to power q. Okay, q naught is also the same, it is the starting state and it is a part of your states, right? It is a subset of q. Your big q has q naught, q1 and q2 in it, and your initial state is a subset of it, it is a part of it. Then f is the set of final states. Okay, so here for this example there is only one final state, right? But there are scenarios where there can be more than one final state. That's why it is mentioned with capital F, that it is a set in itself. And undoubtedly your final state set is also, it is also a subset of q, right? Your final state is also from q only. Okay, so how, this is how you just explain or determine it. This is how you write it, that your machine that is non-deterministic, you represent it with 5 tuples, q, then summation, then sigma, then q naught, and then f. And how your NDFA is different from DFA, there is only one difference, and that is in the transition function sigma. Here sigma is from any state, if you apply any input alphabet, it will take you 2 raised to power q combination of states. However, in case of DFA, what was the transition function for DFA? It was q multiplied by your input alphabet, and that is going to take you to q. So only the difference is between the transition functions. Okay, so how to represent it? Like here DFA, you can also represent it by a diagram which is known as state diagram. The vertices, they represent the states. Okay, so these are the vertices. So these represent the states, and sometimes you call them corners also. If this is a graph, so these are the corners, or you can call them vertices. So states are the vertices of your graph. The arcs are the labeled, arcs are labeled with an input alphabet. Okay, so these are the arcs, and sometimes you call them edges also. So arcs represent the transitions, and they are labeled with any input alphabet, and they take you from one state to the another state, right? And the initial state, how you are able to locate initial state? And I told you that any empty single incoming arc, so this is an empty means there is nothing before it. So an empty single coming arc says that this is your initial state. And what is your final state? Any state with a double circle around it is known as the final state. The final state is indicated by double circles. Okay, so after that we have discussed this thing also, that suppose this is the transition diagram I have with me. Okay, and what input symbol, what input I want to process? I want to process 0 1 0 0. Okay, so this is the input string and I want to process it, and I want to check that if this NDFA accepts it or it rejects it. Okay, so you always start from 0, the first letter of your input. So the first one is 0. Okay, so you are at q naught. Obviously your transition always starts from the start state, that is q naught. And to q naught, if you give 0, what are the possibilities? You can see that if to q naught you give 0, there are 2 states that are generated as output. So if from q naught you give it 0, okay, so the one possibility is you go back to q naught again, and the other possibility is you go back to q3, right? So for your starting state q naught, and for the input 0, there are 2 states that can be reached. One is q naught in itself and other one is q3. So can you see, from q naught, if 0 is given, 2 possibilities are you again come back to q naught, and other one is you go to q3. Okay, so it means this 0 is considered as done, it is processed. Now what next you have to process? You have to process 1. Okay, so if you give 1 to q3, you are here, suppose if you give 1 to q3, can you say here that q3 has no input 1, q3 has only input 0? It means this 1 will not work for q3, so that's why nothing is mentioned about here. So let's talk about the second possibility, that you have reached q naught and you give it 1. Yes, if to q naught you give 1, can you see again two possibilities have arisen here? First one is if to q naught you give 1, the first possibility is you again go back to q naught, and the second possibility is you go back to q1. Okay, so to q naught, if you give 1, one possibility is you go again back to q naught, other possibility is you go back to q1. Okay, so now consider that this one is also processed. Now next is 0. Okay, so let's talk about that. If you give q1 0, but you can see here that q1 is not getting 0 as input, so it means nothing is after it. However, to q naught you can still give 0. Let's check. Yes, if to q naught you give 0, how many possibilities are there? Two possibilities again. You again go back to q naught and you go back to q3. So you go back to q naught or you go back to q3. Okay, so after this 0 is done, let's talk about the last 0 which is left, and let's give it to q3. Yes, we can give it to q3 because q3 has 0 as input. So when I give 0 to q3, I will reach to q4, which is my final state. So it means if I follow this path, this one, q naught to q naught to q naught to q3 to q4, it means in that case my string will be considered as accepted. Okay, but I have to create a diagram for the whole string. Okay, so to q naught, if you give 0, you reach q3, right? And to q3, if you give 0, you reach to q4. But if you give this 0 to q naught, can you see here? I have talked about this possibility. To q3 I am giving 0, but still one possibility is left, that I am giving 0 to q naught. Okay, so to q naught, if I again give 0, it is again taking me to q naught and q3. Okay, but this is the dead end. After that there is no string to be processed. It means only this path is going to give me the final state, and this is something I have discussed in the last class also. Okay, so here consider that you are given in your exam a non-deterministic finite automata. Okay, it means I'm talking about NDFA. So here is an example. So suppose your Q, the set of states, is made up of how many states? 3, right? A, B, and C. Okay, so till now we are talking about states and we are naming them as Q0, Q1, Q2. But there are still possibilities that you can name your states as A, B, and C. Perfect. Nothing to worry about it. Okay. Next, there is your this summation, your input alphabet. It means your input string is made up of only two alphabets, that is 0 and 1. Okay, so your input is of the form of 0 and 1 only. After that, which is going to be your starting state, your first state out of A, B, and C. So your first state is A. It means your A is going to be your starting state. And what is your final state? Your final state is C. Okay, so in exam sometimes you get the examples like this, where you are provided with your set of states, your input alphabets, your initial state. So out of ABC, A is considered as initial state, and out of ABC, the final state is C. Okay, and this is given, and then there is a transition function. Can you see here transition function is missing? I told you that your NDFA is made up of how many alphabets? Total 5 alphabets, but transition function is missing here. So transition function is available in the form of a transition table. Okay, so there are 3 states, A, B, and C, and you can see from here that there are 3 states. Okay, so present state at any time there are 3 states, A, B, and C. Okay, and what will be your next state? That is here, right? And this particular column says that your next state if the input is 0, and this says that your next state if the input is 1. Now let me explain it to you one by one. Okay, so how you create a transition function, I told you already that for this example particularly, so these 4 symbols and this will be already provided to you. Okay, so what you have to do is that you have provided with these 4 symbols and you are provided with this transition diagram, and what will be the output that your teacher is going to ask you. What are my expectations from you? My expectations are that considering this and considering this transition table, you have to generate your finite automata. It means you have to generate the state diagram. You have to generate the graphs. Anything can come. Okay. I can ask you, okay, generate the state diagram. I can say, okay, generate the finite automata. I can ask you, okay, generate the diagraph. Okay, I can ask you, okay, generate the graph. I can use any one term out of it. And all these terms mean same. Okay. So now see here, these are the states. So how you need to create the graph? So you consider this. This is of no use. Okay. Only this is of the use. Okay. So if you are considering that your present state is A, okay, and you give it input 0, your present state, which is your starting state, how it is starting state? Because this information tells me that A is the starting state. Okay. So if my starting state is A and it is given with the input symbol 0, it says that two states can be achieved. Okay. To A, if you give 0, one possibility is you come back to A, other possibility is you go back to B. Okay. Just keep this thing in mind and I will take you to the diagram and I will prove it. If from A you get the input 0, there are two output states that can be reached. One is A itself, other one is B. See here, from A, if you give 0, can you see here to A, this is the starting state. How you make it starting state? You always put one arrow like this towards it. So that will give me information. Okay, student has made this as the starting state. Okay, and to starting state A, if you give 0, it will take you back to A again. So this is one transition. Other transition is if you give A 0, it will take you to B. This is another transition. To A, you give 0, it will take you to B. So this is done. Okay, this with 0 and it will take you A to B. I have done it. Next is to A. If you give 1, it will take you to B. So see here, to A, if you give 1 also, it is taking you to B. Okay. If to A you give 0, even then it is taking you to B. To A, if you give 1, even then it is taking you to B. Okay. So if for any state, two different inputs take you to the final one state, you have to write them with the comma in it. A to 0 gives B, A to 1 give B. Don't do it like this, that A to 0 go to B and then you draw one more vertex, A to 1 go to B. No. If the starting and the ending is same, then you have to write all the input alphabets with the comma. Okay, you can't draw multiple lines between the same. Okay, so A with 0 also going to be, and if there is A with 1 also going to be, then put them with the comma. So this is also done. Next one is from B. If you give 0 input, it is taking you to C. So to B, okay, consider that this is your C. Okay, if B you give it 0, it goes to C. So this is the representative. B with 0 goes to C, but B with 1 goes to A and C. So B with 1, if you give B with 1, so it is also going to C. Okay, so that's why I'm putting it with comma here. But to B, if you give 1, it also taking you back to A. Okay, so back you have to represent with the different line. So after that, the last one, to C, if you give 0, it generates B and C. C, if give 0, right, it generates C also, it generates B also. Okay, and the last one, to C, if you give 1, it goes to C. So C, you give 1, it goes to C. C to 0 also C, C to 1 also C. So if it is same, you just put it with the help of a comma. Okay, so suppose this is a non-deterministic finite automata, okay, and the starting state is Q0 because there is one empty arrow coming towards it, and the final state is Q2. And there is only one input alphabet this time, not two, right? We have till now done all the transitions with the maximum two input alphabets, AV or 0, 1. Okay. But for this, there is only one alphabet, that is A. Here, your summation is made up of only A. Okay. This is the starting state. This is the final state. So this transition diagram is already available. Okay. And there are how many states total? 1, 2, 3, and 4. Okay. And to Q0, if you give A, it takes you to Q1. To Q0, if you give A, it takes you to Q3 also. After that, there is nothing. Okay. To Q1, again, if you give A, it takes you to the final state. So this is a transition diagram available for this finite automata, where Q is, capital Q is made up of how many states? Q0, Q1, Q2, Q3. Okay. What is your initial state? That is Q0. What is your final state? That is Q2. What is your input alphabet? That is A. Okay. Now let's see. Let's do this. Let's suppose I want to process this input alphabet, that is AA. You know that only one input alphabet is available. So your string is only made up of A, right? Because there is only one input alphabet, A. There is no B. It means all the strings that you can check whether is accepted or not will be made up of only A. Okay. So first of all, I am considering two A's and I want to process them and I want to check if this finite automata will accept it or not. Okay. So I am starting from Q0. Okay. So first A will be processed. I am at Q0. What will happen? This A will take me to Q1. This is one possibility. To Q0, if you give first A, it will take you to Q1. This is first possibility. And next you process the second A, and from Q1 you will reach to Q2. This is very good. And by following this path, Q0 to Q1, Q1 to Q0, you can say that this input is consumed, all input is consumed, nothing is left, and you have reached to the final state. So this AA is accepted by your finite automata, this non-deterministic finite automata. Okay. The other scenario, the other chance. Okay. So from A, from this Q0, if you pass it first A, there is one more possibility. Don't forget about it. That from Q0, although you can go to Q1, you can also go to Q3 also. Now I am following this path. Okay. So again, this is the string with me. I am at the first letter. A is processed. And now I am from Q0 reaching to Q3. Okay. After that, still I have one more A to process. And if I process it, can you see I have nothing to go beyond it? No transition after it. There is nothing after it. It means your automata will hang here. Okay. If it is hanging, it means it is rejected. All the input cannot be consumed. Only one letter can be consumed. The second letter will not be consumed. So that's why you consider it as rejected. So an NDFA or non-deterministic finite automata, it will accept a string. When it will accept a string? When there is a computation of the NFA that accepts the string. It means when there are enough states to accept it. For example, here there were enough states. There were 2 states reached and the whole input was consumed and you have reached to the final state. It means it is accepted. Okay. So when there is a computation of the NFA that accepts the string, and you can also say that an NFA accepts the string if all the input is consumed and the automata is in the final state. Obviously, if nothing is left, all the input is consumed and now you are in the final state, only you will consider then that that string is accepted by your non-deterministic finite automata. Okay. When it will reject a string? When there is no computation of the NFA that accepts the string, right? All the input is consumed and the automata is in the non-final state. Suppose there are enough states, okay, to handle your string, but even if all the input is consumed, all the input is used, you still are not in the final state. You still have not achieved the final state. So you will say that this string will not be accepted. This is one scenario. And the last scenario is input cannot be consumed. It means there are not enough states to consume the input. One scenario is that there are not enough states. Your input is still there. You are not able to consume it fully. It means that string will be rejected. Other one is your input is consumed, but you are not able to still reach to the final state. It means still that particular string will be considered as the rejected string. Examples. See, this is an example. So suppose this is the automata that we are talking about, and I will say that AA is accepted by this non-deterministic finite automata. How? So I am here at Q naught. If I process the first A, from Q naught, I will reach here to Q1. Okay. Then I will process the second A. So it will take me from Q1 to Q2. It means this is accepted. If I follow this path, AA will be accepted. However, if I choose the other path, from Q naught, if I apply A, it will take me to Q3. And from Q3, if I check that I still have one more input A, right? So I can see that there is no more states to handle it. It means my input is not fully consumed. So when your input is not fully consumed, you are still left with some input. It means that string is rejected. Okay. So this is accepted. If you follow this path, AA is accepted. If you follow this path, AA is rejected. Okay. So suppose if I have only one A to handle, only one A to handle. Okay. Only one letter in my input string, that is A. So if I follow this path, I will reach at Q1. Okay. And after that, can you see there is nothing left? You will be here at Q1. You are not, although your whole input string is consumed, but you are not able to achieve the final state. You have not reached here. You are just in the middle of nowhere. You are here, Q1. Okay, although your input is consumed, but still you are not able to reach to the final state. It means it is still rejected. Okay, other scenario, you are at Q naught and you follow this path. You use A and you reach to Q3. Although your input is again consumed, but still you are not reached at the final state. It means it is also rejected. So this is explained it together. So A is now rejected. How? If you follow this path, this one, you are not able to reach to the final state. So rejected. If you follow this path, again, you are not able to reach to the final state. So all the possible computations lead to rejection. Let's do this. That now your input string is made up of 3A, 1, 2, and 3A. Okay. So from Q naught, if I follow this path, first A takes me to Q1, second A takes me to Q2. Okay. Although I have reached to Q2, but can you see that my input string is not fully consumed? Okay. I still have one A left. Okay. So I will say no further transition, the automation will hang. So I will consider it as rejected because input cannot be consumed fully. The other scenario, I am here, Q naught, I want to consume it. I have used this path now, Q naught to A, you have reached Q3. Again, you still have two things left. Your automation will hang, your input is not consumed fully, so it will be considered as rejected. So this is here, that with the triple A, both the scenarios will reject it. Okay, so all possible computations lead to the rejection of it. If you follow this path, although you reached at the final state, but still one A is missed, it is not consumed. If you follow this path, two A's are not consumed and you are also not in the final state. So both the computations are rejected. So triple A is rejected by it, right? And A is also rejected by both the possibilities. Only what is accepted? AA. AA is accepted. If you follow this path, so it is accepted. Although if you follow the other path, it is not accepted. But even if there is a single path that will accept it, it means you will consider that it is accepted. So AA is accepted, A is rejected, and even AAA is also rejected. So you can see, and you can say that the only language, I will introduce you with the languages also. This is a full topic, and I will do this language topic with you in future. Okay, so the only language that it is accepting is AA, the 2A. Okay, so just leave this concept if you are not able to get it now, what is language and why you are saying this thing. Just focus that only AA is accepted by it. Okay, now I am telling you that there is this problem with NDFA. I was liking DFA. For one state, one input, only one state was achieved, right? There was one input state, there was any one input alphabet, and you are going to reach to one output state. Everything was so simple. But this NDFA has made everything so complex. Okay. Next thing is that there is a need of just making them equal. I want that my NDFA that is giving me so much problem, I want to convert it into DFA. It means, can I create an equivalent DFA from NDFA? It means I have NDFA with me. I am not happy with it. Can I create a DFA out of it? Yes, I can create. And what is that topic? Equivalence of NDFA and DFA. It means you have an NDFA with you. You are not happy with it. Can you create a DFA, equivalent DFA? Let's do it. Okay. This topic is very interesting, and it is a bit like logical, not conceptual, both conceptual and logical. And such things can come in your paper. Okay, it is in the form of a numerical. You will feel that you have to do some steps, and then you will be able to go from NDFA to DFA. It means in the paper, in the exam, I will give you one NDFA, and you have to follow these steps that I am going to teach you, and then you will be able to generate an equivalent DFA. Okay, so let's discuss this method of converting your NDFA or NFA, which is non-deterministic finite automata, to its equivalent DFA, that is deterministic finite automata. So in NDFA, what was happening, that when a specific input is given to the current state, what happens? The machine goes to multiple states. There are multiple chances, multiple possible outcomes were there. Okay, it can have 0, 1, or more than one move on a given input symbol. Now what do you mean by 0? 0 means that if I will give it some input, okay, maybe nothing is generated, no state can be reached, maybe one state can be reached, maybe 2 states can be reached, maybe 3 states can be reached. Okay, on the other hand, this DFA was so good. In DFA, what was happening? When a specific input is given to the current state, the machine is going to only one state. It was very simple. Everything was very clear, right? So it means DFA has only one move on a given input symbol. And I like this concept of DFA. And now what I'm going to do, I am going to convert my NDFA into an equivalent DFA. Okay, so suppose I have an example. Okay, so I have one automata machine, finite automata machine. Okay, and it is represented by Q, the number of states it has, then the input alphabet, then transition function, then Q0, that is the starting state, then F, that is the final state. Okay, and this machine, this finite automata machine, is actually an NFA. So I'm not going to say NDFA or anything. So NFA means non-deterministic finite automata. Okay, so these 5 symbols I have, and it is a machine, and it is actually an NFA. So NFA means that it actually generates more than one state when any input alphabet sorry, when any input is given to one state. So to one state, if I give any input, more than one chances are there. Okay, and it accepts the language LM. Okay, so just don't worry about that. So language means the kind of strings it accepts. I told you previously that that particular transition diagram was accepting all the languages of the type AA. A was rejected, triple A was rejected, and later on I will tell you that there is a secret behind it, right? AA will be accepted, and there is one pattern that you have to follow. Maybe AA is accepted, all the odd ones are rejected. A will be rejected, triple A will be rejected, 5A will be rejected, and all the even ones will be accepted. Double A, 4 times A, right? And then there is 6 times A, then there is 8 times A. Okay, so these are the languages, the categories of the languages that are accepted by that machine. The sets, all the sets of strings that are accepted by a particular transition diagram or particular finite automata, we can say that this is a language. Okay, so don't just get confused with it. If you don't get the idea what it is, just leave it. Only just consider that this is a finite automata and it is a non-deterministic. Then there should be, it says that there should be, it means it should happen for sure that there should be an equivalent DFA, right? It's compulsion that there should be an equivalent DFA that is present. And how to denote that? By M dash. If it is M, let's denote that equivalent DFA that I am going to convert it into with an M dash. Okay, and it has Q dash as the set of states, sigma dash as the input alphabets, Q naught dash as the initial state, and then maybe the states will change. Maybe in this NFA, A is the initial state, and in case of the DFA that I am going to create, maybe B will be the initial state. So that's why everything I have changed here. Q dash, sigma summation dash, Q naught dash, the sigma dash, and F dash. Okay, then I have to make sure that whatever language this M is accepted, I have to make sure that this M dash should also accept that language. It means whatever language my NFA is accepted, that language should also be accepted by my M dash also. Only then I will say that both are equivalent. One example, suppose this NFA is accepting AA. It is accepting all the strings of the type AA. And I have created one equivalent DFA. I have converted my NFA into an equivalent DFA, that is this. And if this DFA is not accepting AA, it means these two are not equivalent. Okay, it means whatever my NFA is accepting, my converted DFA should also accept that. Only then I will say that both are equivalent. So that's why I have written the language that is accepted by my M, that is NFA, should also be accepted by my M dash. Both the language should be same, right? And even if this thing is not making any sense, just leave it and let's do the steps and everything will be more clear. Okay, so just consider that I am converting it into DFA, deterministic finite automata, where everything is represented with the dash dash dash. Q dash means states, this summation dash means the input alphabet it has, Q naught dash means the initial state it has, sigma dash means what will be the transition function, F dash means what will be the final state. Okay, so the DFA to which I am converting it into is represented by all dash, right? Okay, there was some issue. Let me resume it again. So I was telling you that I am going to convert it into DFA. Okay, and in DFA, everything, all the 5 tuples is represented by dash. Okay, so when I will start creating my DFA, everything will be empty. There will be no state in it. There will be no input alphabet. I have not created any, I have not made any state as the initial state. I have not judged what will be my final state. I have not decided what will be my transition function. So in the beginning, everything will be empty. So that's why I have mentioned that initially the Q dash, which is the number of states, is blank. It is 5. It has nothing in it. Okay. Now, before explaining this, what I want you to do, I want you to do first one example with it, right? And then I will take you to the algorithm. Okay. So suppose this is an NFA with me. Okay. This is one NFA. Suppose this NFA I will give you also to convert it into an equivalent DFA. Okay. So convert the given NFA to DFA. So see here. So this is going to be your starting state. Are you able to figure it out? Yes, because there is an empty arc coming towards it. So this is my starting state. And this Q2 is going to be my final state. And total number of states are Q0, Q1, and Q2. This is my NFA. In NFA, what is Q? Q are the number of states. So Q is Q0, Q1, Q2. What is the initial state? It is Q0. What is the final state? It is Q2. What are the input alphabets? What is summation? Summation is 0 and 1. Can you see? The whole diagram is made up of only zeros and ones. Now we have to work on the transition function for this NFA. Okay. So are you able to create the transition function? Yes. From Q0, if you give 0, you come back to Q0. From Q0, if you give 1, you go back to Q1. So this is the transition function. Okay. So for the given transition diagram, this is the first step. For the given transition diagram, we will first construct the transition table. So this is your NFA. Okay. Now how to convert it into transition table? First, on the left side in the first column, you have to write the states. Can you see how many states are there? Q0, Q1, and Q2. So write them like this. Q0, Q1, and Q2. Okay. And to make it easy, right, for others to understand, whatever your starting state is in this column, in the first column, your first state will be the starting state. Just put one arrow before it, just to represent to others that this is the starting state. And whatever your final state is, just put a star on it, just to represent that this is your final state. Even if you will not put it, it will be okay. But this is a good way of representing that this is the starting state Q0, then there is Q1, and then there is Q2. So you write all the states in the first column. Okay. Now on the first row, what you write? You write the alphabets. So as I told you that there are only two alphabets, 0 and 1. So write 0 first and 1 first. This is the best thing to do, that always write 0, 1 and 1 later on. Now from Q0, how to read it? Now you have to fill this one, this first, this second column, the first row. Okay. So from Q0, if you put 0, you give it 0, where it takes you? Can you see? When Q0 gets 0, where it will take you back? It will take you back to Q0. There is no other possibility. So there is only one possibility. Now from Q0, if you give input 1, where it takes you? From Q0, if you give it input 1, it takes you to Q1. So this is done. Now let's talk about Q1. From Q1, if you give it input 0, see here. From Q1, if you give it input 0, where it is taking you? It is taking you to two states. Q1 on 0 taking you to Q1 also. Q1 on 0 takes you to Q2 also. So this is how I represent it. That Q1 on 0 takes me to two states. Q1 also, comma, Q2 also. It means the set is generated. Right? After that, Q1 on 1 takes you to Q1 on 1 takes you to only one state, that is Q1. Q1 on 1 takes you to one state, that is Q1. Don't consider this one because it is coming towards it. Always consider what is going away from it. Q1 on 1 takes you to Q1. Done. Last one, final state. Q2, if 0 takes you to Q2. Q2 with 0, only one chance, that is Q2. Can you see here?
But Q2 with 1, there are two chances. Q2 with 1 takes you to Q2 also, takes you to Q1 also, right? So Q2 with 1 takes you to Q1 also, Q2 also. Okay, so Q1 first and Q2 later on, right? The second step is, now we have to, now this is the transition table for NDFA. This is sigma because it is of this NDFA. NDFA means sigma. Okay, so this is your sigma, but we are converting it into DFA. Now let's start. Okay, now DFA's transition function is represented by sigma dash. Okay, now we will obtain sigma dash transition. Okay, and from where to start? We will start from Q naught. We will start from Q naught. Okay, so how you represent it? You represent it with the sigma dash. Let's see it. So sigma dash, okay, so represent all the states in square brackets. So first we say that your transition function, if you consider Q naught, your first state, to Q naught, if you give 0, where it is going to take you? I'm repeating that your Q naught, if you give it 0, where it is going to take you? You can get the hint from here. To Q naught, if you give it 0, where it is going to take you? It is going to take you to Q naught. So write it like this. For your sigma dash, write all the states in the square brackets. So now you're generating a new transition function. So for sigma dash, I am considering the state Q naught. So if Q naught gets 0, it is taking me to Q naught. How to prove it? Use this thing. Sorry, use this thing. Q naught when it gets 0 goes to Q naught. Second one, Q naught when gets 1. There are two possibilities only, 0 and 1. Q naught when gets 1, where it is going to take you? It is going to take you to Q1. How to prove it? Q naught when gets 1 takes you to Q1. Okay, so what I am going to do, I am just writing everything in the transition table in the form of this. Okay, now Q naught is done. Now the second for Q1. Now Q1, I have processed Q naught. Now I have to process Q1. So the transition for state Q1 will be now generated, will be obtained. How? Okay, so if I consider Q1 and I will give it 0, where it is going to take me? So Q1 when given 0, where it is going to take me? It is going to take me to two states, Q1 and Q2. So this is how it is written, Q1 and Q2, right? Here I have mentioned that a new state generated. There is one new possibility arised. Previously only Q naught, Q1 or Q2 were there. Now there was some combination being generated. Okay, so whenever there is a mixture of more than one, just write that a new state generated. A new state is Q1 comma Q2. Okay, so to Q1, if I'm giving 0, two different things are generated together, because on giving 0 to Q1, Q1 was also reached and Q2 was also reached. Okay, so I will consider this combination as a new state in my new DFA. But to Q1, if I give 1, to Q1, if I give 1, it is taking me to Q1, the previous state, basic state. So Q1 is also done. Now I'm left with Q2. So to Q2, if I give 0, it takes me to Q2. Q2 on 0 takes me to Q2. But Q2 on 1 takes me to Q1 and Q2. It means everything is normal. Q0, Q1, Q1, Q2. Everything is normal. Only a new possibility. This Q1 comma Q2 is a new state I have to consider. Whenever there is a combination like this, I have to write a new state generate. Okay, I don't have to write it here again because this is the repetition. Okay, so a new state is generated here. Okay, so now let's consider that this Q1 and Q2 is a new state. Q0 was already there. Q1 was already there separately. Q2 was already there. The new state generated is Q1 comma Q2. And if a new state is generated, I have to just check that from that new state Q1 comma Q2, if I give it 0, where it will go? If I will give it 1, where it will go? Okay. For Q0, Q1, Q2, I have already checked that if I will give it 0, where it will go. If I will give it 1, where it will go. But now, as I have considered that a new state is generated, I have to work on it also. That if I will give it 0, where it will go. And if I will give it 1, where it will go. So that's what I have written here. That summation dash, now this is my new state, Q1 comma Q2. Can you see? Previously, I was writing only Q0 and give it 0. Now I am writing that to Q1 and Q2 together as a new state. If I will give 0 as the input, where it is going to go? So I have to write it as the transition function. This is the transition function for NDFA, and this is the transition function. It means I will drive it from that. So I am writing it like that. Sigma of Q1 with 0 union sigma of Q2 with 0. I'm repeating it again. This is sigma dash because it is of DFA. This is the new state generated. Now I'm going to check if I give it 0, where it will go, and if I will give it 1, where it will go. Okay, so how I am going to represent it? I will represent it with the sigma of NDFA, right? That if to Q1 if I will give 0, union to Q2 if I will give 0. I have broken it. I am just breaking it. Okay. So how to write it? To Q1 if you give 0 and union to Q2 if you give 0. I have just represented at sigma of Q1 with 0 union sigma of Q2 with 0. Okay. So Q1 with 0. From where I can get the value Q1 with 0? I have to go back here. Q1 with 0. It is giving me Q1 comma Q2. So I am writing here Q1 comma Q2. And Q2 with 0. Q2 with 0. It gives Q2 only. Q2 only. Okay. So there is a combination of Q1 comma Q2 union Q2. And whenever there is a union between two, you always take the both, just remove the repetition. So both are Q1 and Q2. Which three states we had already? Okay, recording is not starting. Okay, so I had Q0 already with me, Q1 already, Q2 already. From where to check? यहाँ से मैंने I have to check it from here. From where I have created the transition function for dash, that is DFA. This is with me, right? With 0 and 1. Q1 was with me, Q2 was with me, but here a new state was generated. That states 0 and 1 is also with me. Okay, that's 0, 1 and their output. 0, 1 and its output. 0, 1 and its output. New state 0, 1 and its output. Okay. So now let's create the transition function. The state Q1, Q2 is the final state as well because it contains a final state Q2. Okay. So in the DFA, Q0 is going to be my initial state. But what will be the final state? Final state will be Q2 plus the new state generated Q1 comma Q2. Why this Q1 comma Q2 is also final state? Because it has one state which is already final, Q. Okay. So how to represent it? See here, Q0 on 0 takes you to Q0. Q0 on 1 takes you to Q1. Q0 on 0 takes you to Q0. Q0 on 1 takes you to Q1. I mean using this transition function 1, 2, 3 and 4. I have to now create one transition table. Okay. Now Q1 on 0 takes you to Q1, Q2. Q1 on 1 takes you to Q1. You have to just look from here. Q2 on 0 takes you to Q2. Q2 on 1 takes you to Q1, Q2. Q2 on 0 takes you to Q2. Q2 on 1 takes you to Q1, comma Q2. So this is also final state. This is already there. Now there is a new thing. Q1, comma Q2. Q1, comma Q2 on 0 takes you to Q1, Q2. Q1, comma Q2 on 1 takes you to Q1, Q2. Same. Now transition function is generated. Now I am able to create a transition diagram. Q0, Q1, Q2, but there is one more state, that is Q1, comma Q2. Using this transition table, I have created this transition diagram. How? From Q0, if I give 0, it will take me to Q0. Q0 on 0, take me to Q0. Q0 on 1, take me to Q1. Q0 on 1, take me to Q1. Can you see? For any particular input, there is only one state being generated. It means it has been converted into DFA. Q0 on 0 takes you to Q0. Q0 on 1 takes you to Q1. Done. Q1 on 0 takes you to Q1, Q2. Q1 on 0 takes you to Q1, Q2. Final state. Q1 on 1 takes you to Q1. Q1 on 1 takes you to Q1. Right? After that, Q2, which is final state, on 0 takes you to Q2. On 1 takes you to Q1, Q2. The last one, for Q1, Q2, even if you give it 0, it will come back. Even if you give it 1, it will come back. So how it is represented? Even if you give 0 or 1, it will come back. So this is the final transition diagram being generated.